Okay, so this is going to be our 5th video. Hopefully I can get through more than one unit. Unit 6, square roots, functions, equations, and inequalities. Okay, again, this is kind of high. Do you know what you're looking at? Okay. When you're graphing a square root function, while it is true you can take the square root of a negative number using your imagination, you're still setting restrictions on the domain. Okay, well, in this case, you've got a domain. The lowest value that x can possibly be is 0, because you can take the square root of 0. Square root of 0, of course, is 0. So, x can be 0, x can be greater than 0, and x can be has to be less than infinity. So that's your domain. You could actually write this more simply as just x is greater than or equal to 0. And you may see it appear either as an interval such as this, or as a singular inequality such as that. Okay. That having gone through that thought process, remember your square root curve looks something like this. And so, if x is 0, then I'm saying, okay, y is equal to 0 over 5, the square root of 0 over 5. Well, okay, well that's just all 0. So then, the least value that y can be is 0. And it is increasing without bound, just like the x. Once again, it gravitates towards infinity, which is not defined. And so, again, that is logically equivalent. That's what the little 3 equal bars means, to saying y is greater than or equal to 0. And that's it. This one, it's very similar, except you have sort of a vertex type of thing going on. Sorry, I got a little glue on the back. Okay, so if this is kind of in a vertex form, once again, insiders lie and outsiders are telling the truth. And so we have kind of a curve going like this, except this is the point -2, -3. Again, insiders lie, and this is inside of the radical. And so you still have that basic idea of, okay, I'm going up and away from the vertex, and I'm defined at the vertex, but everything else is the same. So you follow a similar pattern here, except instead of starting at 0, you're going to start at -2 is less than or equal to x less than infinity. And then, of course, this is logically equivalent to saying x must be greater than or equal to -2. Likewise, with the range, instead of starting at 0, you're going to start at -3. And so you say -3 is less than or equal to y, which is less than infinity, which is logically equivalent to saying that y is greater than or equal to -3. Here again, insiders lie. So we have -3 inside and +4 on the outside, which means you have a vertex point of 3, 4. And so x has to be greater than or equal to 3, and y has to be greater than or equal to 4. And I don't feel like showing the interval between 3 and infinity and whatnot, because it's well defined, and we're not answering an interval notation. Interval notation is one of those fun things you get to learn in pre-cal or in Algebra 3. It's going to be beautifully painful when you get to learn that. Oh well. Tasty math, fun notation. Got to love it. Okay. Practice problems. You have a radius formula. It can be used to find the radius of a cone with a volume of v and a height of h. If the cone's radius is 5 centimeters and its height is 12, what is the approximate volume? Okay, so this is where life gets fun. They gave you the formula. They gave you the bits of information. You have to solve for the unknown. The thing that's even more ridiculous about it is they gave you a volume. They gave you a volume of a formula that you already know from tax, but that's okay. So, radius is 5, height is 12. So plug and chug. So we're saying, okay, the radius is 5 is equal to the square root of 3 times the volume, which is an unknown, divided by pi times the height, which we know to be 12. Okay, well that's going to be fun. We're just going to backwards engineer this. In order to get to the v, I have to cancel the square root. Well, what cancels the square root? Square. So we now have 5 square. We square this side and we square this side. So we're like, okay, 5 squared, squared, square cancels root, and root cancels square. So now we have 5 squared is equal to 3v over 12 pi. Well, what's the opposite of dividing by 12 pi? Multiplying by 12 pi. So we have 25, which is 5 squared, and we're going to multiply both sides by 12 pi. Now, notice I have not actually tried to evaluate pi. There's a reason for that. Pi is an ugly irrational number that I am not going to evaluate till the very end. So this cancels this, and so now we have 25 times 12 pi is equal to 3v. Before I do anything else, rather than multiply 25 and 12 pi, which would give me some big, hideous, ugly number, I'm going to divide everything by 3, because 3 and 12 have a common factor. So I'm going to divide everything by 3, or rather this by 3. So now I have v is equal to, now 12 divided by 3, of course, is 4. So now I have 25 times 4 times pi, which is 100 pi. Now, if my solution in the multiple choice is not in terms of pi, then I will evaluate pi. If I don't have to evaluate pi, I'm not going to. So, that was fun. Next one. Given the equation, solve for y in terms of x, which means, hi, can you get y by itself? Groovy beans. Okay, so I've got a square root, I've got an 8, I got a y, and I got 2x. Okay, first thing I want to do is cancel the square root. What cancels the square root? Squaring. So, this cancels the root, so now I have 2x over y is equal to 64. Now, I do not like having my y in the denominator, so I'm going to multiply both my left and my right side by y. This cancels this, so now I have 2x is equal to 64y. Okay, well, to get y by itself, I just divide by 64. So now I've got y is equal to 2 over 64 times x, and you can reduce that because 2 over 64 is kind of like 64 divided by 2. Well, 64 divided by 2 is 32, except instead of it being on top, it's going to be on bottom. And that was fun. All right. Once again, hi, can you solve y in terms of x? Well, once again, I need to cancel my square root. Cancel my square root by squaring. So now I have 4x minus 2y is equal to 36. At this point, it's something an Algebra 1 student can do. Subtract 4x from both sides. And now you've got negative 2y is equal to negative 4x plus 36. Notice I use the commutative property of addition. You'll see why in a moment. Now, to cancel the negative 2, which is a multiplier, I am going to, you guessed it, divide. All right, so I'm going to divide both sides, or rather every term, by negative 2. So now y is equal to, 4 divided by 2 is 2. A negative divided by a negative is a positive, so I have 2x. 36 divided by 2 is 18, but a positive divided by a negative is a negative, so it's 2x minus 18, final solution. So that was fun. Okay, 9 minutes down. Let's see if we can have some fun with Unit 7. A blank is a horizontal line, y values, that the graph of a rational function approaches as the x values approach negative infinity or positive infinity. How very asymptotic. An asymptote, specifically a horizontal asymptote. Now, there are 3 scenarios. Basically, you find your horizontal asymptotes based on the degrees of the numerator and denominator polynomial functions. So if I look at our first example, here we have 2x squared. That means it is a second-degree polynomial. I do not care about the constant -11. Here in my denominator, I have x squared plus 9. So they're both second-degree polynomials. Okay, as x gets bigger and bigger and bigger and closer to infinity, the difference between -11 and positive 9 becomes so small, so slight, that it really doesn't matter. So in the end, because the degrees of the numerator and the denominator are the same, because these are both x squared terms, your horizontal asymptote is the ratio of your coefficients. Well, in this case, your numerator coefficient is 2 and your denominator coefficient is 1. So your horizontal asymptote is that y is equal to 2 over 1, or quite simply that y is equal to 2. That's it. Now, I'm going to do the middle one in a sec. Just because it's a little bit more fun. Let's do the second one. Here we've got a second-degree polynomial in the numerator and a third-degree polynomial in the denominator. Because the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is where y is equal to 0. Now, again, if all else fails, graph the stupid thing and you'll be able to see it. Now, this is the fun one. As far as you are learning in Algebra 2, because the degree of the numerator is greater than the degree of the denominator, the horizontal asymptote does not exist. This is true. Horizontal asymptote doesn't exist. You actually have a orthogonal or a diagonal or a transverse asymptote that exists, and the way you find it is you do the polynomial division between the numerator and the denominator, and the quotient function is the diagonal asymptote. But you will not be asked to do that on the test, so that'll be fun. So for the next part, a removable discontinuity. Sounds like something out of sci-fi, isn't it? All right, a removable discontinuity is a hole or a break in the graph of a rational function. It occurs when the values of the x make the numerator and the denominator equal to 0. Simply put, it cancels out when a equation is simplified by factoring. A blank is a vertical line created by the values of x in the numerator. A rational function is equal to 0. Unlike horizontal asymptote, the graph can never cross or touch a vertical asymptote. And by the way, that was the answer. Gotta love it when the answer is in the question, don't you? Hopefully there'll be some examples on the other side, because that's always fun. And there are? Okay. All right, we're doing good on time. Okay, so basically what you need to do is you need to factor everything, basically. Okay, so let's sort of back it up. I'm going to start with the last one. Okay. So your domain. Is there any value I could put in for x, positive, negative, or 0, that would make this 0? And the answer is no. If x is 0, 0 plus 1 is 1. Not dividing by 0, perfectly valid. If x is a negative number, the squaring of it makes it a positive number, and you're adding. So no way to get to 0 there. You get a positive number there. Again, no way to make the denominator 0. So your domain is either you think of this as all real numbers, or you think of this as from negative infinity to positive infinity. That being said, as x gets bigger either as an absolute value or as a positive value, as the denominator gets bigger, the net value gets smaller. It looks something like, so you start at 50, and it's going down, 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 down. Gets closer and closer to 0 without ever getting there. and then 50 goes down, 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 down. Doesn't really have an asymptote because it can be anything, so it's sort of a little point. And so your range is, it's never going to cross over 0. And so really, you're going from 50 to 0. So here's 50 here, here's 0. And you're never going to cross over because you have a positive divided by a positive all the time, because the denominator never becomes negative. And so your range goes from 0 to 50. Now, the function is defined at 50 because where x is equal to 0, y is equal to 50. So y is between 0 and 50. It is defined at 50. But it doesn't matter how large that denominator is, you will never actually get to 0. So it is not defined at 0. That's important, because I can guarantee you on a question like this, there will be one where it's double defined. Okay, so that was fun. Let's work our way back. This one, hi, did you recognize that this is 1 over x plus 1 times x minus 1? Did you know that we could factor this out? Okay. That being said, you have two discontinuities, and neither one of them can be removed. And so the easy way to describe this is just to say that x cannot equal either positive or negative 1. Okay, now, this is where life gets a little fun. You've got, and it's kind of, talking about the range is going to be a little bit on the painful side, but bear with me. Your numerator is always positive, okay? Now, if you think about it, you've got two little points right here. Here's negative 1, here's positive 1. Okay, your quotient function, if I've got negative 2, or negative 3, or negative 4, or negative 5, negative 2 minus 1 is negative 3. Negative 2 plus 1 is negative 1. So you have a negative times a negative, which is a positive. So everywhere to the left of negative 1, this is going to be positive in the denominator and positive in the numerator. Make sense? Okay. Let's say I've got between let's just say I've got 1/2. 1/2 plus 1 is 1.5. 1/2 minus 1 is negative 1.5. That means this denominator becomes negative over here. Because if the denominator is negative and the numerator is positive, whole thing's negative. Now, let's keep going. 1 and beyond, say I got 2. 2 minus 1 is positive. 2 plus 1 is positive, so that's positive times a positive. Makes the denominator positive, makes the whole thing positive. Okay, so this makes your range kind of all kinds of funky screwy. But, you know, it just means that in certain parts, you're going to go down to negative infinity. In other parts, you're going to go up to positive infinity. And so you'll see when you graph this thing, it'll look something like this. Which means it'll go down to negative infinity, it'll go up to positive infinity, and it'll get really, really close to 0. But the one place it will never be is 0. And so very often it's easier to talk about this in terms of what it isn't rather than in terms of what it is. Actually, I was being kind of an idiot, because if I look and say, oh, my degree of my denominator is 2, my degree of my numerator is 0, then my horizontal asymptote is 0, which is the one place I can't be. So that was fun. This one, again, degree of the denominator is 1, degree of the numerator is 0. So again, my horizontal asymptote is at 0. So if my HA is that y is equal to 0. My range is that y cannot be 0. My domain, again, I'm looking for a value of x that my vertical asymptote is that x is equal to -5. Insiders lie, and in this case we're inside the denominator. And so where my asymptote is, my domain is not, and so x cannot equal -5. Okay, top three ones, you're just factoring this out. Okay, 3 and 9 are both divisible by 3, so you say, okay, this is 3 times x plus 3. So that was fun. Now you've got x squared plus x minus 6. I know that this is going to be x plus 3 times x plus 2. Or, sorry, minus 2. The reason I know it's going to be plus 3 and minus 2 is typically they're not going to give me a factor up top without something to cancel on the bottom. They might, but they might not. Okay, so this tells me I have a removable discontinuity because this would cancel or remove this. Most common mistake, people say, oh, x plus 3 cancels x plus 3, and so therefore my removable discontinuity is that x is equal to 3. There's just one problem. Insiders still lie, and so it is not that x is equal to 3, but rather that x is equal to -3. Same with my vertical asymptote. My vertical asymptote is where x minus 2 is equal to 0, and so, again, insiders lie and x is equal to 2. Similar idea for the other two. Let's get to it. So we've got x squared plus 8x plus 15. Factors of 15 are 5, 3. 5 and 3 add up to 8. So we have x plus 3 times x plus 5, and that factors very nicely. Next one, factors of 8 that add up to 6 are 4 and 2, and in this case they're both negative. So we have x minus 2 and x minus 4. Negative times a negative is a positive. Negative plus a negative, still negative. None of these cancel. So the removable discontinuities, there are none. And you have two vertical asymptotes, one at x is equal to 2, because insiders lie, and then another one at x is equal to 4. You have a horizontal asymptote at 1 over 1, because of the two coefficients are the same. This one, you would have a horizontal asymptote at 3. Notice they have the same powers. Ratio of the coefficients is 3 over 1. Didn't ask you for a horizontal asymptote, gave it to you anyway. This one, let's factor it out. We have 3 times x squared minus 9. Well, that can be factored further. We'll get to that in just a sec. Factors of 18 that have a difference of 3 are going to be 6 and 3, so this is probably x plus 6 times x minus 3. Well, at this point, half of y'all stopped on the first test and thought, oh, they're too different. I can't factor anything out, in which case you got that one wrong. What you were supposed to do was to recognize that x squared minus 9, and I'm going to write this down here, factors into x plus 3 and x minus 3. I would still have the coefficient 3 on the outside because I didn't cancel anything yet. Now I have x plus 6 and x minus 3. So the x minus 3's would remove. You would say that x is equal to 3 because insiders lie, and the remaining asymptote is x is equal to -6. And that was probably the two most painful units of the year.